Hello everybody, and welcome to this OxTS webinar on why it is important to use an INS on a mobile scanning vehicle. This is going to be given by Paris Austin, our business manager here for OxTS Survey and Mapping. If you have any questions throughout the course of this, you can type them down in the chat box, and we will try to get back to you during the webinar and we'll answer them more thoroughly at the end. So without further ado, here is Paris.
Thank you, Jake, and thank you everyone for joining today. So as Jake said, we're going to cover this subject of why to use an inertial navigation system on a mobile laser scanning vehicle. And to do that, we're going to cover very briefly about who OxTS are, so a little bit of history about the company and what we do, why you should use an INS in order to articulate some of the reasons behind our content today, and then some of the challenges and the solutions that we offer to those challenges for mobile mapping when using a laser scanner. So OxTS, as in terms of the background to the company itself is 21 years of age this year, and during that period of time we have sold predominantly to automotive R&D teams who are developing vehicles, initially for vehicle dynamics testing, where acceleration and angular rates and heading, pitch and roll were really key, and more nowadays with ADAS and autonomous vehicles, where position of the vehicle and the direction it's pointing is key to validating the performance of onboard sensors. One of those sensors that has come very much to the forefront of both automotive and survey applications is LiDAR, and so we're going to cover some of the things that are a key factor in deciding why you should use an INS for use with this sensor. So we've always made what we refer to as a red box all-in-one solution. So you can see the Survey Plus here on the right is one of our flagship products, and we developed the IMU, the navigation engine and the hardware combination in-house, and we calibrate it at OxTS as well. And more recently, thanks to a focus on survey industry applications, we've also developed a piece of software called OxTS Georeferencer, which merges your LiDAR and INS data in order to produce a point cloud, which can then be used to create maps of any form. So when we talk about an INS or inertial navigation system, what we mean at OxTS is a combination of an inertial measurement unit and a GNSS receiver. So what used to be GPS only is now a combination of GPS, GLONASS, Beidou, Galileo, and we are in all of our products using GPS and GLONASS as standard, and more focus is coming onto the multi-constellation systems. With the IMU, we combine 3 gyroscopes and 3 accelerometers, and we build that into an OxTS designed IMU, which we calibrate and put into all of our products. The good thing about pairing these 2 systems together is that they both compensate for the weaknesses of the other while playing to their own strengths. So while GNSS is what we might refer to as an external sensing method, which requires a line of sight to the satellites that are going to give you your triangulated position, the IMU is only aware of its own intrinsic motion. So the 2 systems sense a completely mutually exclusive form of position and displacement between one packet to the next. And what that means is that they can work very well in tandem. The way that we combine the data is through a Kalman filter that is also designed within OxTS and developed over the years. And what that allows us to do within the Kalman filter is to intelligently decide whether to use data or reject it, how much weighting we should give to a given measurement, and what the conditions are in real time, so that the user can have full transparency on how the decisions have been made, whether there's satellites in viewed but rejected, or whether they're all being used because the conditions are perfect. That is all available to the user so that you can see how the system has come to that decision. And we will refer to a tightly coupled navigation engine in this presentation, which effectively combines the system at source, the IMU and the GNSS, rather than tacking them together at the end. What that means for you as a user is that the data output gives you nanosecond accurate time thanks to the GPS output and the atomic clocks that are running on those satellite systems, 3D global position, so latitude, longitude, and altitude, and then 3-axis orientation, heading, pitch, and roll. And also, like I previously mentioned, you get a lot of status updates that come from the Kalman filters, real-time calculations. So you get things like position accuracy in 3-axis, heading, pitch, and roll accuracy, number of satellites tracked versus used, and everything like that. One of the questions we get a lot, or have got a lot in the past, and maybe for some of the territories where this technology is still an emerging technology in terms of the adoption rate, is why can I not just use a GNSS receiver? So we use a GNSS receiver. We use Novatel, Topcon, and U-Blox in our range of products. And on their own, they're very capable devices, but GNSS has its own weaknesses, which is the reason that we have built our system around the IMU. And the GNSS receiver is a very good device for capturing absolute position on the Earth when conditions are good. But there's a few reasons why we would say a GNSS receiver on its own is not sufficient. The first one is the fact that when it boils down to it, a GNSS receiver, if you had a single antenna system, would be able to give you position and velocity and heading as long as your vehicle was on the move. If you didn't have any motion with the vehicle, then the heading would be effectively void because you need a direction of velocity in order to give you a heading vector. And a single antenna GNSS receiver cannot do that. If you step up to a dual antenna GNSS receiver, you can get heading regardless of speed, but it will still be susceptible to the same outages that a single or triple antenna system would have. So if you went under a tunnel or under a bridge or through a tunnel, then you would still get a dropout of complete data absence during that period because you're relying on the line of sight vision of satellites in order to give you those updates from the GNSS receiver. So you can achieve full 6-axis position and orientation. You get your 3-axis position, latitude, longitude, and altitude from a single antenna GNSS receiver, but you cannot get heading, pitch, and roll unless you use a triple antenna system, and even that still has its downsides of data dropouts. So that brings us on to point 2, which is the fact that an INS can give you continuous output regardless of the conditions. So you will not get 98 Hertz or 50 Hertz or 1 Hertz if your data is not coming in from GNSS. You will get the constant rate of data that your INS has been sold to you at. So if you've purchased a 100 Hertz system, from the point that system initializes, you will get 100 Hertz data all of the time. The accuracy of that data will drift over time if you lose GNSS for an extended period, but the fact that you still get data through a tunnel under a bridge is a factor of an INS that cannot be competed with when using a standalone GNSS. And then the third point is an INS running a Kalman filter is going to be more accurate than a standalone GNSS system. Some GNSS receivers do run their own Kalman filter in order to try and create a feedback loop that can rule out unexpected data, but it doesn't have another information source that we have or any INS has from the IMU. So that inertial measurement unit can give you a validation of whether or not a GNSS update is unexpected. And by unexpected, we mean something that is not along the same trajectory course as what the IMU would say you are based on the accelerations the system has seen. So the GNSS can only make the best of the data it has, and if it has nothing to validate itself against, it's going to give you a solution when it can or no solution if it has no data to work with. Thanks to the IMU's constant intrinsic data rate that doesn't care about line of sight to anything, you're able to get that constant data rate with a validation loop that allows you to validate whether your GNSS is good or bad and scale the IMU when it is good and let it steer the INS trajectory when the GNSS is bad. So the way that we achieve that in terms of the hardware, this is our Survey Plus product, which is our kind of flagship INS. And we achieve accuracies through exploiting the hardware in different ways. So absolute position accuracy will always come from the GNSS receiver. There is no other sensor on the planet at this time that can give you 1 centimeter absolute position relative to the Earth frame without using GNSS. You might be able to achieve similar levels of accuracy in other methods, but it will all be relative to a start point or a calibration point. So GNSS is essential for people who are working globally or even just nationally, who are comparing data to other companies or collaborators who have collected similar data sets, and they want to overlay the data on top of each other. And that is easily achieved through GNSS. Heading, pitch, and roll come from a combination of GNSS, when you have a dual antenna system, gives you heading accuracy, and then one of the 3 gyroscopes in the system will help supplement the heading accuracy. And then pitch and roll come predominantly from the gyroscopes in the X and Y axis, and are supplemented further by the accelerometers in the system, because we can use where gravity is in order to calculate how out of plane the INS is with respect to the Earth frame. One of the other benefits of the hardware and the implementation of the hardware is that we can use an odometer, so a wheel speed sensor, and that can help to further reduce drift of the IMU when it is navigating without any assistance from the GNSS. And then finally, all of that data, all the raw data from the GNSS, the IMU, the configuration, that is all stored on board automatically so that you can post-process and optimize the settings retrospectively. So this real-world example is just to articulate the difference between a GNSS-only sensor, so a receiver working on its own, and a tightly coupled INS. So in this example, this GNSS plot in red is not a separate standalone GNSS receiver. It is the receiver that is inside the Survey Plus, and then the light blue line is the actual INS solution from the Survey Plus when working in a tightly coupled navigation engine. The key points that we want to highlight is, because of the intermittent output of GNSS, doesn't mean that these spikes are continuous updates from point to point. If it doesn't mean there's 100 updates between this line and this line. It just means that we may have dropped GNSS signal here, received one update here, and then received another update here. So this may have been 10, 20 seconds where there were no GNSS updates received on the trajectory along which the vehicle was traveling. And so in that period, the INS is steering itself based on 100% IMU data. And in short periods like that, it's more than capable of doing so. If this GNSS data was coming in 100 meters off to the side of the actual true trajectory for several minutes, then this blue line would start to drift away from the true trajectory over time. But because these outages are intermittent, we can use the short-term stability of the IMU in order to achieve that full system accuracy. And then at the bottom of this diagram, or this Google Earth plot, you can see an event where multipath was having an effect. So you can see there are actually multiple updates. You can see the curve on this line, so there is more than one update from the GNSS. Updates like this is update to update is causing the spikes, but you can see a continuous stream of updates that have come in here, and that is almost always due to multipath. So a reflective signal from a building making the GNSS receiver's antenna believe that that signal was coming from a satellite that was further away, and that then means that your triangulated position comes in at a different location. The key point here is the IMU can categorically say that it didn't experience a lateral acceleration that should cause it to move tens of meters over to the side. And so the INS can reject that, and the Kalman filter can say that the GNSS is not operating to spec. And you can also see the effect on mobile laser scanning is, if you try to use this red data plot in order to georeference LiDAR data, you would have absolutely useless data in terms of a point cloud that you could then use for post-processing. With the blue plot, you can achieve repeatable overlays of the same trajectory driven multiple times, or you can drive multiple directions around the same target so that you get increased density of point cloud without increasing the iterations or the numbers of versions of the building or object that you want to survey due to an inaccuracy of the navigation solution that you're using. So this can stretch to dozens and dozens of applications, and we've pulled out a few of them here, but for us to understand what people are using the products for or what they would be interested to use the product for, we are trying to make the most of this webinar platform. So we're just going to pose the question to the audience: which applications are you most interested in when doing your data collection? So what would your use of the product be for? And there's 5 options because that's the limit of the webinar question platform. But if I just step through the 5 that are there, when we refer to asset management, we mean things like continuously operating work site where jobs need to be raised and damage is caused and repairs need to be assigned to certain responsibilities within the site. And so you want to intelligently track that data and report it using a 3D point cloud that turns into a map. We've got 3D reconstruction, so that is effectively the digitization of buildings and real world scenarios in the digital form for any number of end uses. And then survey of highways, we mean things like road quality, road surface quality, road sign recognition, lane markings, that kind of thing. And then BIM, or building information modeling, where you extract features from buildings in order to determine volumes or the state of quality or things that you're going to use in order to make intelligent decisions elsewhere. So the baseline between buildings or things like that. And then HD maps for autonomous vehicles, I think, is self-explanatory. So thank you for that. We're going to move straight on. Mobile laser scanning then faces challenges because of the environments under which we and you as users will want to use it in. And that inevitably means that GNSS conditions are never perfect. So that's where an INS really adds its value. If you were doing all of your data collection in open sky, an INS would still add value because of the heading, pitch and roll addition, but it wouldn't improve performance past that 1 centimeter accuracy. What the INS can do in these conditions that we've listed here is it can help you achieve the highest level of accuracy for the longest time period. So we're going to cover what those kinds of the effect of those poor conditions can have on the data and how we can improve it. Some of those solutions specifically then that we offer, one is our navigation engine, which is we refer to as GXIX. That is a tightly coupled navigation engine solution, and we'll explain what we mean by tight coupling on the next slide. We have combined data post-processing and advanced smoothing, so forwards and backwards combination of processing directions and then merging the 2 data sets to give you the best possible outcome. And then lateral and vertical advanced slip, which is an automotive derived feature but can be applied to survey applications to achieve a much higher level of accuracy. And then bore site calibration is a solution that we have developed very recently and launched to the market in March of this year, and we're just going to cover that briefly. So tight coupling, to start with, we'll explain what loose coupling is, and then we'll build on top of that. So loose coupling is when you take the output from a GNSS receiver, so the latitude, longitude and altitude, and then take the IMU data's acceleration and angular rates and integrate them to give you heading, pitch and roll. What that means is that the IMU is giving you the orientation data and the GNSS is giving you the position data. And in periods where GNSS data is very poor, the IMU will effectively integrate its accelerations in order to give you displacement change. But what that means is you will disregard the GNSS data completely if it believes in the Kalman filter that the solution is not good from the GNSS. So when we tightly couple the data, we do not use the GNSS receiver's calculation for latitude, longitude and altitude. We actually take the pseudo range and carrier phase data from each satellite and we generate the latitude, longitude and altitude incorporating the accelerations and angular rates from the IMU at the source. So you combine effectively 9 inputs, 3 from the GNSS, 3 from the gyroscopes and 3 from the accelerometers, and you generate the latitude and longitude and altitude, heading, pitch and roll from those inputs. And what that means is you can achieve much higher level of accuracy for more period of your data set. There's two parts then to how GX-IX operates. Maybe that's obvious that GX and IX are two separate parts, maybe it's not. But here we explain GX is effectively our tightly coupled solution for merging the inertial data with the GNSS data. And what that allows us to do is overcome some of the shortcomings of GNSS when it operates on its own. The one feature that we have is called inertial relock, and that reduces the error search that you have to start from. So instead of having a cold start after a GNSS dropout, you have a warm or hot start, as is referred to in some data sheets when you're buying an INS. And then IX is our other half of our tightly coupled navigation engine, and what that allows us to do is work in particularly challenging environments. So if anyone is familiar with GNSS positioning in general, you need at least 4 satellites to position yourself on the global frame. And if you drop to 3, you would no longer be able to tell where you were on the Earth, because there would be 2 potential solutions at any one time, and one of those would be likely somewhere inside the Earth's core, which is a non-viable latitude longitude to give to the end user. So what IX does is, once you have achieved a position lock in 3D space, if you then drop to 3, 2, or 1 satellites, because we are continuously using the IMU to continue your position tracking, we can continue to use individual satellites and their range values in order to maintain our position on the road or in the sky or wherever you're using the system. So that's a really powerful thing, because then it reduces drift of the IMU over time. And it means that when we regain lock on satellites, it means that we're having that hot start every time. So just to articulate a little bit more clearly what inertial relock is and how it works, if you were to enter a tunnel, if you're looking at this diagram in the top right, if you were to enter a tunnel at time 0 on this graph, and over time your system was drifting because there was a complete outage of GNSS data, then a loosely coupled system would grow over time. The system will not have been scaling the IMU as tightly as a tightly coupled system will, so the error will be slightly higher anyway. But the key point is that with inertial relock, you may emerge from the tunnel shortly before this point, and the loosely coupled system would still take time to relock onto satellites, because it always has to do a cold start as to where those satellites are in the sky, especially when you're working to RTK integer centimeter level accuracy. With inertial relock, because we are using the inertial data to prevent the drift of the system, but also we know within, say after 60 seconds, if position drifted 10 meters in real time, then we know that after that 60 seconds, we emerge from the tunnel, we are within 10 meters in real life of where the INS says we are. And so that reduces our search sphere to a 10 meter radius sphere. Whereas with a loosely coupled system, the GNSS receiver is effectively starting from scratch, and you will have as many as multiple kilometers as a search sphere in order to triangulate your position. So it doesn't matter if this is a tunnel that's 60 seconds long or a bridge that is 1 second long. If you drop satellites on a loosely coupled system, it takes more time to relock onto your RTK position. And with the tightly coupled solution, it's a lot quicker. What that means in real life then is you get this increased overall performance in terms of boosting the amount of time of your data set that you will spend in the higher accuracy mode, so RTK being the highest accuracy. And so we've, in an example data set, jumped from 84 to 94%. So there's a boost there, but also you spend less time with no solution at all. So the period with no solution is a period where the IMU is drifting freely. So you want to minimize that as close to 0% as possible. And what that means in terms of the average data error over the entire data set, it drops the data error from 12 and 10 centimeters respectively on horizontal and vertical error down to 3 and 5 centimeters, which is almost the levels of specification as a perfect open sky system. So it really does help when you're going under multiple obstructions, or if you're working in tree-lined areas where you're getting sporadically good data mixed with interference data, this tightly coupled system can really help. So post-processing as a concept is not something specific to OxTS, but it's something that we have a solution for that we use. And there are multiple features to it. So one of the big positives of post-processing is that you can optimize your configuration. So even if you didn't get something right in real time, you can go back in post-processing and you can change lever arms to your antennas, you can change the orientation in the vehicle. So say if you installed the INS1 direction and you told the navigation configuration that it was pointing 180 degrees the opposite direction, you would get very poor real-time performance, but you could post-process it and correct that orientation offset so that you could get the best data out with the raw data you've logged. The second positive is that you can process with base station data so that you can avoid any dropout in real-time data corrections, and that will always be a very strong positive for post-process. You're not reliant then on mobile data correction signal if you're using the internet or local radios. And you can use up to 255 per processing run. So that could be 20 base stations from one base station for 20 hours of the day in individual hour-long files. Or it could be from 20 unique base stations if you've done a particularly long baseline test. So you can always use the closest base station to your vehicle at any time, and the system will automatically select which is the closest. One of the biggest benefits of post-processing is the ability to process in backwards and forwards. So this diagram articulates what we mean by combined post-processing. So if this again is an example where we enter a tunnel at time equals 0, and this tunnel is 60 seconds long, over time the real-time output would start to drift and drift and drift exponentially because of the 6 IMU sensors all drifting randomly. With combined processing, we can reverse the processing direction and process the data as if we're entering the tunnel at the time when we exited in real time. And what that does is improve the error to much better than 50% error because of that exponential growth. So at t equals 30 on a 60-second period in a tunnel, that error would be significantly reduced. The other benefit of combined processing is that if your forwards and backwards solutions complement each other very closely, then that gives you a very high level of confidence in the Kalman filter that everything is being calculated very accurately, because it's very unlikely that the TIS systems with different events leading into the same instantaneous moment in time would ever result in the same calculation unless the lead into that event was accurate as well. And so because of the way the Kalman filter works in terms of the build-up of errors, it is minimizing errors the whole time if that is the case. The final benefit of post-processing is a feature that is something that OxTS offer specifically, and that's a feature called advanced smoothing, and we'll cover the benefits of that on the next slide. But basically, there can be step changes between the forwards and the backwards solution when you process, because the lead into the event where they merge can be significantly different. So advanced smoothing prevents there from being a step change and effectively applies a filter to smooth the data out. So this real life example is with advanced smoothing turned off and on. So you can see on the left, this was a data set that was collected with a ZNF profiler, a laser scanner that ZNF produced, and an XNav INS. And in real time, the GNSS conditions were quite poor because of this obstruction. And also there was a tunnel in the period of time after this session as well. So in combined processing, the forwards and backwards solution differed quite a lot. With advanced smoothing turned on though, you can see from the lane markings that everything is very smooth. There is no step changes like there are here, where you can see the lane markings are shifting left and right of each other. And what that means is if you try to use this result on the left for any classification of points in your point cloud post-processing, if you were identifying lane markings autonomously, this would break the output because you may not have a consistent gradient of the lane, and so it would consider that to be a new line and that to be a new line and so on. With advanced smoothing though, you get the continuous nature of the data, and while the lane markings are a very obvious way to see that, that would apply to walls and features everywhere, where you want to see the consistent stream of that data rather than have any step changes in it. So I mentioned at the beginning advanced slip. This is a feature that was derived for our automotive customers in the past, but the benefit of it is that with just a couple of measurements that you will measure before data collection, you can get a lot of improvement to the data. So what we tell the user, this is the software that asks you to effectively enter a lever arm from the INS measurement point to the center of your rear axle and the center of your front axle. And what that can allow us to do is basically work out in the firmware the difference between the INS's mounting point and the mounting orientation compared to the vehicle's forward, lateral and down axes. And so that can then optimize the output of that red box to match the vehicle as closely as possible. And so that means that you will get the most repeatable data. If you drove 2 ways down the same road and there was a camber on the road, you want your INS to match that of the vehicle so you get the true roll angle of the vehicle. And these features enable you to do that while simultaneously reducing drift in other situations. So in a scenario where GNSS data is not perfect, advanced slip can also help you because it prevents any drift on the vertical axis of the system, which is where 3D position accuracy is the weakest. It can prevent that from leaking into the horizontal frames. And so you can see in these pie charts, the key goal is to spend as much of this data set in the yellow quadrant or section. And you can see without advanced slip, we spent 50% of the data set in this mode. With advanced slip turned on, with the same raw data file, the processing resulted in 65% position time spent in the integer position mode, and so that boosts the amount of time we've spent with better than 5 centimeters accuracy. So to actually show you the real life data, we broke this data up into 2 sections where GNSS was good and GNSS was really negatively impacted. So this was a drive from our office to the local town, and then this period was where we drove into a multi-story car park and back out. So you can see there are some positives on position improvement, but this is only an improvement from 4 centimeters to 3 and 2.7. So there's improvements, but it's negligible in terms of overall accuracy. But when you go into poor GNSS conditions, it significantly improves the drift. So you're getting almost a 4 times improvement on vertical drift, and you're getting a kind of almost 2 times improvement on horizontal position drift. And that is because we've prevented that vertical position from leaking effectively, and we can maintain the vehicle's axis level to gravity and using all of the accelerometers to their kind of highest effect. And it means when you emerge from that multi-story car park, where you have previously you would have had this error search to find your true location on the planet, you would have reduced it to this much as well. But that would mean that the inertial relock works better as well, because that error sphere is reduced in size. So we've got a second poll question, which we would like to ask, which is, which environments would you be looking to complete your data collection? So there's a mix in our software, if anyone has ever used it. We have 3 options for the user, which is open sky, some obstructions and frequent obstructions. And what we mean by this is generally, if you're in open sky, you trust GNSS first and foremost, because you believe if it says it's in RTK integer, then it's true. If you go to frequent obstructions or the halfway house, which is some obstructions, it will blend that kind of belief between GNSS and IMU, and it will lean towards trusting the IMU slightly more. But because you're not believing that 1 centimeter accurate GNSS system, it will lower the overall estimated accuracy of the system. So you might only achieve 5 centimeters accuracy in frequent obstructions, but at least you will have a very robust system that you can trust more than you might have if you've told the system to believe GNSS completely and then driven into an dense urban environment. Okay, thank you very much, everyone. So the last point before we move on to any questions, if anyone has any, is foresight calibration. So the whole point of this webinar is to articulate why an INS is of value in a mobile laser scanning application. And one of the key points in that application is that you align all of your sensors on your vehicle to be in the same coordinate system. So you might be able to measure by eye the difference between the INS and the LiDAR to a coarse angle, but you will not be able to measure by eye to kind of down to the levels of specification of the INS itself. So if your INS is giving you 0.03 degrees of accuracy on pitch and roll, there's no way that we would expect a user to measure by eye the 0.03 degrees what the physical mechanical alignment is. So it's really important that you use a data-driven method in order to calculate that, and that's what OxTS have developed that we released earlier this year. So the key point, and we'll come on to this slide, is without boresight aligning your two systems, your LiDAR is going to have one coordinate system and your INS is going to have another one. And when you start working at longer distances, very much like the boresight alignment of any gun sight or anything where that kind of boresight concept comes from, you will begin to diverge more at longer distances, and it will be a negligible difference at short distances. So in this data example, this is a cross section of a road near our office, and then this is the side of a building that was under construction. You can see that the red and the blue line, which is two passes along the same road in different directions, you can see that the data diverges from one from the other in a systematic offset way that is growing over the range away from your vehicle. If you pay attention to this line here and we show you the boresighted data, this is the result of having a boresighted system. So you get no double vision, you have data that is overlaying on itself perfectly, so that you double the density rather than double the number of objects in your point cloud. And it means that then you can start to make a lot more intelligent decisions, and you could drive this route multiple times and get multiple versions of the same location for that building or for that object at the side of the road or that curb or that lane marking. So it's really important to take that into consideration. And OxTS's method for doing that uses these retroreflective targets, which you can kind of see an outline of in these examples. So this survey was executed on a UAV at 50 meters altitude. So the exaggerated nature of the double vision in those targets, there are only two targets in real life showing up 4 times. When you calibrate the system, it compensates for this angular misalignment and you get this result. So this is the exact same raw data, but boresight calibrated. So it's just by applying 3 different angular offsets of heading, pitch and roll relative to the LiDAR, you end up getting improved data with the same raw data. This example on the right is the same data as the left example, but it's without the filtering based on reflectivity. So you can see before the 2 targets show up kind of smeared across the bird's eye view, and the 2 vehicles in the top right show very unclearly as well. So when we boresight the data, exactly the same raw data from the same point of view, you can see that the targets appear clear and square, which they were in real life, and you can see one example of a very dense version of those 2 vehicles rather than 2 versions of the 2 vehicles. So Jake's going to be running a webinar on how to complete a boresight calibration next Tuesday. So if you've got the time, it's well worth signing up to that webinar next week. So just to finish then, and then we'll take any questions. We think, or we hope we have covered today why an INS is superior when compared to a GNSS-only system or even a loosely coupled GNSS IMU. And it's essential for getting the most out of your system in terms of repeatable navigation data so that you can execute your mobile laser scanning application to the highest level of accuracy, because almost always you will be delivering the results of this data collection to your own end customer. And so it's really important that you can put your guarantee that the quality of the data is that high level. So tightly coupling the data is another reason why to use an INS rather than individual sensors that you've pieced together. And that data can be further improved using post-processing forwards, backwards, combined processing, and the advanced smoothing technology as well. That covers the kind of third point I was saying. And then lastly, that bore site calibration, whether or not it's INS plus LiDAR or INS and cameras, you need to make sure you consider the offset between those sensors both linearly in an XYZ sense and heading, pitch and roll offset as well, so that you can ensure there's no errors in your system, that you have no idea where the source of those errors are from. So last question, and then we'll take any questions if there are any. We're just looking to understand what point of their mobile mapping work are people at. So are people using exclusively static survey, or are they using existing technologies, either our INS already or using another competitor INS? And then there's two other options that we see at the moment as being viable solutions in some environments, and that is, one is photogrammetry, so using a camera plus some photo stitching software like Pix4D, or using SLAM plus IMU and LiDAR in order to create a local point cloud that is accurate relative to itself. Or are you just looking to learn, which we're more than happy to help if that is the case. Okay, so that's the end of the presentation. So if anyone had any questions at this point, then please do write them in chat, and Jake will come back to you, or I'll try and answer them on this call now.
Yeah, thank you, Paris. So if you do have any questions, just write them down. So we have a question here. So can you use a triple antenna with an INS or one of our INSs?
The answer is no to that. We only have dual antenna systems, but all of our systems are dual antenna as standard. And the reason for that being, because of the IMU, we would see no discernible benefit from using triple antenna for pitch or roll, and the conditions under which GNSS conditions would be poor, so the obstructed environments or things like that, that would drop out in a similar way, and so we don't get a added benefit versus the performance of the gyroscopes and the accelerometers for those things. But what we do use the dual antenna for is to improve the heading, because we cannot use gravity in order to improve our heading output. So the dual antenna GNSS gives us really good heading performance in low speed or even static vehicle work. So if you're stopping at traffic lights or stopping just because you've parked the vehicle for a period, the dual antenna system will keep your heading from drifting over time, whereas roll and pitch during that period of staticness will not drift at all because of the use of gravity. So there's no benefit when pairing our INS with triple antenna systems.
Okay. So I think that's all of our questions. So if you do have any more, you can just get in contact with us. You can see on the slide there how to access our website, different things on it, and to get in contact with us. And yeah, I think we can end it there.
Okay, thank you everyone.
Yeah, thank you everybody for joining.
And just to say, just the slide that we're on, we will send the recording round 24 hours from now. And if you would like access to any of these slides, then do get in touch. And all these hyperlinks will take you through to the website to learn more about the products as well.
Mm-hmm.
Okay, have a nice day, everyone, and thank you very much.